How are you doing?
I'm good. How are you?
Yes, please has a volume up.
I'm good. Can you hear me?
Yes, we're hearing you, is but a little bit small.
Oh, okay.
And
Mm.
I suppose I really satisfied with this, the Islamabad, the Pakistan culture, and for especially food,
Oh,
really
great.
fantastic. I realize over 50, and
Name
your
there or
food is
not?
better than pizza.
Oh, name is there or not?
Wait a minute, please. Uh, the speaking volume is please up. Yes, please say it again.
I said, Mr. Name. Did you met with him?
Wait.
Name.
Okay.
No?
Yes, say it again.
Name.
Name.
Mr. Name.
Yes, name
Name.
is yes. He will present.
He, oh, he will present. Okay. But
Yeah.
he's not there physically, or he's presenting from Karachi, I think.
Uh he in person here, I think.
Oh, he's in person there.
Yeah.
Okay, great.
Yes. How's your life in the Chicago?
Oh, it's amazing. Great.
Amazing.
In Yeah, my kids are now enjoying more,
Yeah, that's great.
Yeah.
Yes, this our the APAN, the LOC member, LOC, the local organization is the yesterday move our loom because
Oh.
the originally our loom is so smaller than here, and they
Mhm.
the find out is the APRP is attending members is the bigger than they guess, so they change
Okay.
the loom is the bigger size. So
Mm-hmm.
the next speaker is Laz Ketimus. You know him, Laz Ketimus?
And no, I don't know. He's from NNL, right? I
Yes,
never met him.
ANL. He
Yeah.
originally is the participant is Globus, and
Yeah.
currently he the research for this quantum network. And today
Mhm.
he, as a keynote speech, the quantum network is what his the research topic. And I already introduced you, and one of my the great the partners is the working for is Fermi Lab. So and he wanted to know. Oh yes, yes. Look at that. Yes, yes. He
Hi,
is
Andrew.
large Ketimos is keynote
Hi.
speaker.
Very nice to meet you, actually.
Nice to meet you.
So you are from Pakistan. You are at Fermi, and I'm here.
Yeah, actually, I wanted to be there, but unfortunately, because of some reasons, I couldn't.
Sure.
Next time, hopefully. But when you will be here, hopefully we'll meet.
Yeah. So I'll be back this week, actually. So we can connect sometime soon. Yeah.
Okay.
Sure, sure.
Okay. Yes, I wish to the you and is Razi is make friendly, and I want to make a chance to the meet online or offline and to discussion our research topics and it's I think it's very the good the topic meetings. The ANL,
Mm.
the globals, and the quantum network, and even though you are the security or a photon, okay, I'm not sure.
Okay.
Yes, I
I'm
just
not
forgot
sure.
it.
Yeah.
And ASI Plus is several part he involved is the network, SDN, and the
Oh, great.
security,
Great.
AI,
Yeah.
and even though you are Bitcoin,
No,
the
no,
currently
not
he
bit.
manages big data.
Just playing with Bitcoin.
Yes, already he involved our the APRP and Asia Connect project.
That's great. That's great.
Yes.
So which group are you with at Fermi?
I'm working in USCMS.
USCMS. Okay. Sounds good.
Yeah.
Okay, it's time.
Yeah. Please.
Okay. Good morning, Andrew. How are you?
Oh, you're muted, I think.
Okay.
Sorry about that. Oh, good.
Yes. You look like good. Thank you for joining this. So what time is there?
2 p.m.
2 p.m. Oh, okay, it's the reasonable time.
Yeah. So I've done all my morning meetings and can actually spend the afternoon on APAN.
Okay. Okay. Let me start. Is the 9 o'clock is the our APRP working group start time, and I want is a little bit the brief introduce the APRP working group. Okay, let me introduce myself to you, and this is the APRP working group. The APRP meeting is Asia Pacific Research Platform, and since 2018, so our working group is aimed to provide to the ASEAN regions, which the regions are as we have. I think we have a lot of and very smart brains, but we don't have enough computing resources. So research platform meaning is the high based on this high bandwidth distributed HPC. And we want to using NN, such like TAIN or the APAN was each countries they have on their the international or the domestic education and the research network, and we want is a combination among the participant countries, and then establish the research platform based on the Kubernetes, and it means that is the Kubernetes can support and provide is the Docker Hub. Docker Hub is we can share our computer resource as a virtualization, slicing or something like that. So and then we started very small steps. But the last year, and we awarded the last and 2 years ago we awarded this 10 project to make the prototype to how to establish the ASEAN regions, how to deploy APRP working group. Today we the session one is the four the presenters. First one is the Asif Raja from Fermi Lab in the U.S. He belonged to this big data managing and between the U.S. and the European the physics data. And the second thing is the quantum network. Raji Ketemos, Dr. Raji Ketemos, he came from this ANL from US, and he introducing of the whole the quantum network technology issues as a keynote speaker. And the fourth the presenter is the Dr. Kyu Kim. He introduces the index project in Korea, and it means that is inter data centers, how big data transfer and how the big data management. And the last one is data sharing infrastructure across Northeast Asia and supercomputing centers for open science. On me, I explain about this new project for related our APRP working group. Let me start is the Asif Raja. Are you ready? And start your presentation.
Yeah, let me share my presentation. Can you see my presentation? Is it visible?
Not yet. Is okay. Go ahead.
Okay. Good morning there. I cannot see all the guys, but good morning to all of you. My name is Asif, and today I'm going to present about the Fermi's high-speed networking R&D efforts for the high-lumi LHC era. I'm working here at Fermi in the network department, particularly in networking R&D for USCMS. This is the outline which I'm going to present today, starting with the overview of CMS and USCMS, and then discuss something about the high-lumi LHC and the data challenges and networking R&D efforts at the Fermi and our WAN connectivity transition up to 2.4 terabits. So let's start with the overview of CMS and the US CMS. If we talk about the CMS, CMS is basically, I think you all know about the high energy physics experiments, and one of them is the CMS. And the purpose of CMS is to study the proton-to-proton collision at the CERN's LHC, Large Hadron Collider. So you can see the detector in the right side of the picture, CMS detector, which is detecting the proton-to-proton collisions and recording the data. And that data is basically, transmitted, worldwide for the physics analysis. Over 200 institutes from 57 countries and more than 3,300 physicists are basically part of this experiment. And if you're familiar with the LHC tier architecture, CMS itself having, worldwide 7 tier 1 sites and more than 50 tier 2 sites. And the CMS compute needs are basically covered by using the WLCG grid resources, which is basically the global collaboration of more than 170 computing centers and approximately, you can say, more than 1 million CPU cores it is providing and more than 1 exabyte of storage, including the disk and tape. So this is all about the CMS. And if I talk about the US CMS, where I'm working here as a networking R&D part, particularly for US CMS, Fermi is one of the largest tier 1 center here in US for the CMS experiment, along with the 7, the tier 2 sites. And the purpose of the Fermi is to enable the US physicists to take the, the leadership role in the physics world, particularly in the CMS. So if we talk about the CMS experiment and other LSC experiment like ATLAS, ALICE, and the LSCB, so the current time, at the current stage, we can say we are currently in the LHC era. But in future, in 2029, we will have the new era, which is called the High Lumi LHC era. What is the High Lumi LHC era? I will discuss that, but it is changing the dynamics of the scientific workflows. So for the to enable the High Lumi LHC era and to cope up the challenges of High Lumi LHC era, there are lots of R&D efforts for CMS in the scientific community is ongoing. And we also working at Fermi Lab for USCMS, some, efforts, but particularly I'm working in the networking field. So therefore we are working on the R&D efforts of the networking related, so which I will discuss later. So what is the High Lumi LHC? Whenever we are talking about the High Lumi LHC, this is basically the next phase of the science harvest at CERN, which will start in 2029. And for CMS, particularly for CMS experiment, it is going to generate the huge amount of data by 2029. You can compare in this right side table that how many, the number of collisions today we have around 9 billion, but in the era of High Lumi LHC, it will become 56 billion. Similarly, the total per year petabyte of storage data that will be generated. Currently, we are generating around 20 petabytes of data yearly, but in High Lumi LHC era, we will have 600, petabytes of data per year. So that will be huge. You can see 20 times or 30 times more than today's. So to fulfill these requirements, we need to expand or upgrade our infrastructures particularly for the scientific workflows. So for that, scientific community designed some data challenges events. And the purpose of those data challenge events are to demonstrate the capability of infrastructure. Infrastructure means the compute infrastructure, storage infrastructure, and the network infrastructure. And these data challenges are basically the scaling challenges, that how much scalable your infrastructure is to transfer, to demonstrate the transfer of the data from storage to storage, production data. So every year they set up some targets. You can see in the right side in the bottom table, I show here the Fermi's target, where we have to upgrade our link. For every data challenge, we have to upgrade our link at least whatever the target is given in this table. So in the last DC24, we have to upgrade 200 Gbps link, through which they can demonstrate the data transfer from CERN and other tier ones and tier twos. They can engage and they can utilize this link for the data. So on top of that, this is a WLCG collective graph, cumulative graph, where you can see in March 2024, we had the data challenges. And you can see that collectively, all the experiments are achieving more than 300 gigabytes per second, on the throughput you can see. So this is, we can imagine how big it will be in future high-lumi LHC era. So next, the data challenge, which will be, scheduled in 2026, and we have to reach around the 60% of the target. That is basically the 400 Gbps link we should have, and we have to demonstrate the more data should be transferred in that DC26. As I said, the high-lumi LHC era will be huge. So for that, there are a number of R&D efforts in the scientific communities are ongoing, including in the storage, compute, and network technologies. Some peoples are working on data management softwares like Rusio, and data transfer services and software like FTS and X2D. At Fermi, we are also working on these things as well. Storage technologies like Dcache and EOS and networking. Because I'm working particularly in the networking R&D, so I'll emphasize on my projects which I'm going to discuss here. Whatever the R&D efforts we have here at Fermi Lab, particularly for the high-lumi LHC networking. So if we talk about the networking requirements for high-lumi LHC and networking infrastructure requirements, if we discuss today's era and we see the scientific workflows, they are looking network as a just an opaque infrastructure, and scientific peoples are just injecting the data, and they are thinking that it should be up to the quality of experience whatever they expecting, right? And we are just increasing the link capacity, and we are thinking that it will be as per the quality of experience, but that's not the case. We need efficient utilization, which is very important, and and deal the network as a first class resource particularly for the scientific workflows. So that's basically the vision of our networking R&D here at Fermi Lab. So considering this vision, we have some projects on which we are working here at Fermi Lab. One of them is the Sense Rusio architecture. Basically, this is the ESNet initiative, but we are, as a USCMS, we are the part of this test bed. Another is the Noted architecture, which is a CERN's the initiative, but we have also the test bed here at Fermi Lab, and we are part of that collaboration. And the third one, which is our own initiative, which is basically the AI-based traffic classification, and we are working with in collaboration with the ESNet. Before moving to these to details of these projects, I would like to show you this. This is basically the core LHC network, the connectivity providers. We know that all the tier ones and tier zero is basically the CERN, and all the tier ones are connected using the LHC OPN network, which is a dedicated optical network for the tier ones. Means all the tier ones are connected with the LHC OPN. And if we talk about the worldwide tier twos connectivity, all the tier twos are connected with the LHC1 VRF by using the virtual routing forwarding mechanisms. And We also have some regional network, like we have PAN in Pakistan, and here in US we have the ESNet 6, which is a regional network provider, Internet 2. In Europe we have Giant, and other parts we have Scenic also. So these are the core LSC network providers. But that's not enough. As I said, we need more to utilize these networks in an efficient way. For that, I said that we are working on the Sense Rusio network architecture. Basically, this is uh, the end-to-end, SDN-enabled network architecture. This sense architecture is creating the overlay network, end-to-end QoS guaranteed network. It provide you the flexibility of prioritize your workflows, scientific workflows as you want. It create the overlay networks. It sense elevate your network to as a the first class resource. Means we can automate, we can orchestrate the network as we want using the APIs. So it create, you mean to say, the end to end the connectivity with certain QoS guaranteed path. So this is what the sense is, and this is the sense Rusio. Basically, Rusio is the data management software in scientific workflow, and FTS is file transfer service. It's a file transfer service, and XRUD is also similar. So Sense can provide interoperability among all these software stake and interacting with all these software stacks whenever we need to create an end-to-end path, a QoS guaranteed path, a prioritized path where we have to transfer the huge amount of data. In the right side, you can see for every flow, you will see the different lines with the different colors. So it is creating a different path, end-to-end QoS guaranteed path using the right side workflow, where multiple, the sense components are involved: sense orchestrator, sense network RM over the WAN, and sense site RM, which is located at the sites. And this is basically our test bed here at Fermilab, where we have storage nodes. We have the sense site RM configured here locally. We have some data transfer node. We have some XRUD nodes are configured. And also we have our network connectivity, which is connecting via the ESNet. So we are participating in this architecture, and we are trying to explore the possibility to evaluate the better ways to manage the CMS data transfer in a more efficient way. So main purpose of this test bed is to, evaluate the better ways to manage our CMS transfer, that how our CMS data is going to be transferred between amongst all the US CMS sites. Our collaborators are mainly the ESNet is leading this project, but we are working as a collaborator with them. USCMS, all the USCMS sites are also part of this collaboration as well. This is the topology of all USCMS sites, where you can see we are connected via the ESNet, and Fermi as a tier 1, and all the other sites like Purdue, UNL, UCSD, Caltech, Vanderbilt. So all these are the USCMS tier 2 sites, and we are trying to transfer the data among all these sites and utilize the sense architecture for this purpose. The next project that we are working on here at Fermi also is a part of Fermi. It's basically the NOTED. It's network optimized transfer of experimental data. Basically, it's also SDN optimized file transfer service, but it is using the logs of application and finding if there is a congestion in the path, then it creates an alternate path. Particularly it's working with the FTS software, as I discussed before. It's a file transfer service. So Noted is working with the FTS, watching the logs of FTS. If there is a path, the network congestion on this path, and then it create the alternate path, and then it shift the flows on that path, on that alternate path. So we have some servers here at the Fermilab, which is a part of this Noted testbed as well. Last time in SC23, we demonstrated the Noted as well. Similarly, since we demonstrated in SC23, DC24, and soon we are going to demonstrate in SC24 as well. This is how the noted is working. Let's suppose we have the LHC1 LCOPN path as a primary path from Fermi to Sun for data transfer. And if the path is going to be congested, then noted is monitoring the FTS, and then it provision the sense path. And then once the sense path is created, it transfer the flow from red one to the green one, and your flow will be transferred and it will not be congested anymore. And our third, effort, which is related to the AI-based technique, we are trying to work on the traffic classification by using the ESNet high-tech services. This is basically the new service which deployed by the ESNet at their end. You can see this is the Fermi topology, and HT is basically the high-tech service that is deployed by ESNet and capturing all the packets, all the CMS data here. All the science data, you can say, not only CMS Dune and CMS, both data are captured here at high touch, and then it is going to be stored centrally in a database of the ESNet. And what it is doing, basically, it is providing the service of the flow deciliation, means your all packets are captured, but it's summarized in a flow, small flows. We do not worry about the large and huge amount of storage requirements. And once we have these small flows, then we will have microscopic services through which we can dynamically select the network flows, and we can process it further for traffic analysis, for ML or deep learning related things, or some feature extraction, some classification, some traffic patterns, whatever you want, right? What we are using, why we are using here at Fermi Lab, because if we talk about particularly for the CMS experiment, we have different sort of traffic of CMS, like streaming traffic that's generated through the XRootD, and we have file transfer traffic that's generated through the FTS or XRootD. Then we cannot distinguish in a naked eye. So we required, some services like ESNet high-touch services to capture and summarize the flows, and then based on those summaries, we can analyze and predict that what is the requirement of the bandwidth for the streaming traffic, what is the requirement of the bandwidth for the file transfer traffic, and other applications as well. So this is the purpose, that we should have to classify the traffic based on the AI patterns. So this is an initial stage right now. We are working in collaboration with the ESNet, and we are working on some to train the models, AI models, using some techniques like RNN or CNN, and then we can figure out that we can predict that, okay, this amount of traffic might be required in future for streaming, and this amount of traffic and this amount of throughput required for the file transfer. So this is the main purpose of this project here at Fermi Lab. And finally, I would like to, as I said, that we are moving into the terabits per second network. Fermi already upgraded our, WAN connectivity with the help of ESNet. We are connected with the around 2.4 terabits per second. You can see in the red boxes. We recently installed the Arista router, which is the debuffer router, and support the 4 to 800G technology. And we have link aggregation of the 4x400 and 2x400 with at our border router. So this is the connectivity transition of the Fermi right now. But as I said before, that just increasing the connectivity is not enough. We need to explore some technologies. We need some R&D in the network, that how we can efficiently utilize these, the link capacity in future. So that's what we are working here at Fermi Lab. And that's all from my side today. Thank you very much. And if you have any question, any comments, you're welcome.
Thank you for your presentation. Anybody question about that?
A very nice talk. This is all very relevant. I mean, maybe we should actually have a longer conversation offline. But one question that comes to my mind is, So in the noted, you said like you're going to monitor, and then when there is a congestion, you're going to use sense. Why not use sense right from the beginning?
Yeah, actually, noted is not, it's separate from the sense, right? It's totally separate, but it complements sometimes the sense as well. Let's suppose you have the LHC OPN path only from CERN to Fermilab, right? We have OPN and you have separate LHC1 path. And tier 1 to tier 1, you are transferring from tier 0 to tier 1, means CERN to Fermilab. And there is some congestion is, noted by the noted. And then it will create the path, it will shift to the LHC1 again. We do not need sense for that, right? So if we have, but in the Fermi's case, we have the same, link for the LHC1 and LHC OPN. Therefore, we use the sense, path to create the separate circuit using the sense. Otherwise, the main concept of the noted is to use the LHC1 between the tier 1s and tier 0. And if there is a congestion, then you can shift that part to LHC1 and utilize the LHC1 part. So that's basically the concept of the noted. You are right, we are not dependent on the sense. Sense is a separate entity and noted is separate as.
Okay.
Thank you. I have one comment. As you know, this big data era is already started 10.5 years ago for globally. So the Formulab and as spoken by this Asif Rajas, its contents is the highest big data, the managing, transfer, and the handling, and between US and the Europe. Switzerland is the laboratory. It means that is that transfer and managing is based on this intercontinental. So basically, those technology and those contents are very important to enable the APRP, the research platforms on the poor area and the popular area. And all those kind of things is based on the managing this big data traffic. Thank you, Asif.
Thank you.
Thank you. See you. And the next presentation is the keynote speech of APRP. It's very hardly invite him. Dr. Asif, Dr. Raz Ketimus, he came from the Argonne National Laboratory in US in Chicago, and he working for this grid project, and the invent is Globus, and he the expert for this the big data transfer through this Globus platform, and currently he the introducing about this quantum network. The why we handle this, why we meet this quantum network. In the near future, obviously, in the near future, the quantum network technology is the very important keyword in the IT area. So the reason why and APRP, the research platforms, is sometimes it's a quantum security technology and the quantum network issues.
Oh, okay. Thanks a lot. Okay, wonderful. Thanks, Jiang-Un, for the wonderful introduction, and thanks everyone for being here. So I'm going to talk about, basically I'll start with a brief introduction to quantum networks, and then I'll introduce Argonne Quantum Network. It's a quantum network that we are building at Argonne National Lab. And then I'll talk about some of the quantum network demonstrations that has been done so far from our group and from others from all around the world. Then talk about some of the current challenges for quantum network. Then I'll talk about some ongoing projects that utilize the Argonne Quantum Network and other links that we have at Argonne. And then I'll summarize and take some questions, and we can do some discussions afterwards. So first I wanted to start with what quantum communications is all about, right? So essentially it started with the goal of making classical communication more secure, right? The QKD, the quantum key distribution, which many of you may be familiar with it because it uses the principles of physics, right? It's actually used to create inherently secure keys. Say, for example, the quantum signals are weak, I mean, if somebody is eavesdropping on the link, it's easy to find out, right? So the keys, rather than using like the current, if you look at the current security, it's actually based on complex mathematics, right? So it relies on NP-complete problems, and if you want to decode the key, it will take forever even using the largest supercomputers, right? So rather than relying on complex mathematics and the need for using a huge computer to decode, and it will take forever, so the quantum keys, they rely on the principles of physics, right? So that's why it's inherently secure. So there are like commercial products that are available, right? So that you can use to generate quantum keys, but then there are limitations to it, right? So the quantum signal, you cannot put that through amplifiers, right? I mean, so if you look at the classical signals, once every, like, I don't know, 100 kilometers or so, something like that, right? Somewhere around that ballpark, you need amplifiers. You need amplifiers to amplify the classical signals, but the quantum signals cannot be put through the amplifiers, right? So because of that, you need quantum repeaters, and we don't have any quantum repeaters yet. So because of that, there is a distance limitation, right? I mean, so there is a distance limitation. So the quantum keys, you can distribute up to like 100 kilometers, 130 kilometers, something like that. So that's the limitation, but the quantum communication goes beyond that, right? I mean, so the QKD is sort of well established, even though there are some limitations. So we want to look at quantum communications beyond the QKD, beyond the quantum key distribution, right? So if you look at the quantum computing technology, that's still at a very preliminary stage, right? So if you look at quantum computers, the largest quantum computers these days are have 100 qubits, I mean, which is hardly enough to do any complex problems. I mean, even to solve tie problems, it's not enough, right? I mean, so you need millions of qubits. So one of the things that quantum networks can help is connect these quantum computers, right? So connect smaller quantum computers to form a larger quantum computer, right? So that's what we call by distributed quantum computing. And then also quantum networks has applications in quantum sensing. Quantum sensing is supposed to be powerful than classical sensing, and then if you actually are able to gather data from multiple sensors, so if you are able to do distributed quantum sensing, that's supposed to be even more powerful, right? So those are some of the applications of quantum networks. So, but then the thing is, we need capable quantum networks, right? So that's, again, quantum networks is still in a preliminary stage, but we want to advance the state of the art. So just for those of you who are very new to this, don't know much about quantum computing or quantum networking, just wanted to briefly introduce what a qubit means, right? So qubit is the basic unit of quantum information, and it's a two-dimensional complex vector, right? So the difference between like qubit and the classical bit is it's the qubits are probabilistic, right? So it can be it's hard to say what state it's in, right? I mean, so when you measure, it boils down to one or two states, but it can be in an in-between state until you measure, right? I mean, that's what some people call superposition. It can be in both state 0 and 1, but that's very confusing. But the thing that I want you to get from that is it's probabilistic, right? I mean, so until you measure, you don't know what exactly the state of the qubit is, right? So, and then there are different types of qubits. I mean, the two key qubits, right? I mean, it's flying qubits. What I mean by flying qubits is photonic qubits. So photonic qubits are attractive because you can actually produce that in like a room temperature, right? And then like it's easy to communicate. So the photonic qubits are attractive from that perspective. But then you don't really get to do computing with that photonic qubits, right? So you basically need to convert them to matter qubits because there are like few platforms. People are exploring different platforms for quantum computing, but it's still not clear which technology is going to win out, right? I mean, so there is superconducting based platforms, ion traps, neutral atoms. So these are all matter qubits, right? So, and then another key thing, if you want to understand like quantum computing and also quantum networking, the entanglement is is a key phenomenon, and that's a fascinating phenomenon. You don't have an equivalent of that in the classical world, right? So you may actually have heard that three physicists got Nobel Prize for demonstrating this phenomenon of quantum entanglement, right? So what exactly is quantum entanglement, right? So it's a fundamental concept in the quantum information theory, right? And so what I mean by that is, let's actually take this example to just show you, demonstrate. I've simplified this, but just for understanding purposes. Say if you are in, when two particles are independent, right? So how they behave, when they are independent, how they behave, when they are entangled, how they behave. This picture actually shows that. So when they are independent, so they have equal probability, like meaning, so you can be in, like the system can be like a circle, and I mean, let's say it can have two different shapes, right? I mean, circle and a square, and then so the thing is, you have these four probabilities, right? I mean, so the two particles, so one in circle, so the system 1 is in circle state, system 2 is in square state. Likewise, there are four possibilities, and they four have equal probability to be in that state, right? In one of those combinations. Whereas if two particles are entangled, then they either both of them are in circle or both of them in square. You don't know which one, but so they are dependent. Even if they actually split, I mean, so you entangle two particles and you split them apart to a long distance, right? So even then, they have this dependency. So that's the phenomena of entanglement, and that actually makes the quantum communication interesting. And so still, to be honest, people still don't know all the applications that you can create when quantum networking becomes really available, right? I mean, but then even when you actually, if you think about the classical network, when they created the network, they didn't imagine all the applications that we have now, right? And so the hope is that there are few applications that we are envisioning now, but when the network becomes a reality, there will be much more application that we are not imagining now. So I did talk about some of the applications, distributed quantum computing, quantum sensing, but there are other things as well. In quantum key distribution, we talked about it. And then there are some other things as well where you can actually even actually speed up the classical communication, and also like it can actually help you to do a much more precise clock synchronization. So with that brief introduction to quantum networking, I'm going to move on to talk about the Argon quantum network, right? So at Argon, we have a campus scale quantum network wherein we are connecting 5 different buildings, right? So we have some devices, we have different platforms. So there are physicists working on different kinds of platforms. I mentioned about the different kinds of matter qubit platforms, superconducting, ion trapped, neutral atoms, right? So there are physicists working on those kind of qubits. So we are basically connecting those different platforms using a fiber-based network, right? So and then we have a hub where we have an all-optical switch, and then we have a single photon detectors. The thing about quantum networking is like, so you're basically transmitting a single photon, right? I mean, so the single photon has a state in it, has information in it. That's what you're transmitting. So you need single photon detectors, and you need entangled photon source. So you need to create entangled particles, right? So that can be used to. So one other phenomenon, fascinating phenomenon, is the quantum teleportation, right? So what I mean by that is, so I mentioned about the quantum entanglement. So you entangle particle, you actually move that particle to, like, let's say site A and site B, right? They are at a distance, right? So then what you can do is, so these two particles are entangled, which means they are dependent on each other. Now you can actually transmit an arbitrary quantum state from A to B without physically transmitting that state. you still need to transmit a classical information, but you're not transmitting the quantum information physically through a medium. So that's what is called a quantum teleportation. So since you still need to pass on a classical information, the information still cannot move faster than light, but it's still a fascinating phenomenon because you are not moving the state physically over a medium, right? So you can basically, once you have entangled particles, you can demonstrate quantum teleportation. So this phenomena of quantum teleportation has been demonstrated, right? So the idea here is, again, so even though the quantum teleportation has been demonstrated, this demonstration was only at a photonic level. But you need to teleport matter qubits, right? So that's what we are striving to do. So anyway, so we want to use this infrastructure to do those demonstrations. So we've already demonstrated entanglement distribution on this network, but we want to use that to teleport quantum states, right? So this is what we did, actually. So we were able to distribute entangled particles between two different buildings. And what we also demonstrated was, even on a single fiber, we were able to use different wavelengths and actually distribute multiple pairs of entangled photons between two systems. So then, so the thing that I talked about was the argon quantum network, and the argon quantum network is actually connected to a Chicago-wide, so what we are calling as a Chicago metropolitan quantum network, right? So my colleague Ashif actually was giving the talk earlier, right? So he's from Fermilab. So we have a strategic advantage in the sense that Argonne and Fermilab are quite close to each other. They are both in the Chicagoland. They are only like 30 miles away. So no other labs are that close to each other. Maybe Berkeley and SLAC, but none of the other labs are close to each other, right? And we also had an advantage in the sense that back in the 90s, there were a lot of dark fibers that were laid when the classical internet was picking up, and when we were actually looking at, it actually goes before my time at Argonne, but my boss, Ian Foster, and others, Rick Stevens and others, actually, they did a demonstration called I-Way, right? Information way, right? So that kickstarted the distributed computing and grid computing for science. So when they were doing that project in the 90s, they actually got several fibers laid, and some of the fibers between Argonne and Fermilab were not used. They remained as a dark fiber, they were not laid, right? So I mentioned that the quantum signals are very weak, right? Which means that it cannot really co-propagate with classical signals. I mean, I shouldn't say it cannot, but it needs some careful calibration if you really want to coexist, and it's still not clear how much they can coexist. So people are studying that phenomenon. So can we actually have classical signals and quantum signals go on the same fiber? So since it's early and there is no clear demonstration of this coexistence yet, so it's better to have like dedicated signals for quantum communication now. So for that, the dark fiber really helps. So we were actually using that dark fiber between Argonne and Fermi, and we also have fibers going from Argonne to University of Chicago, which is also again like roughly 30 miles from Argonne, and we also have fiber going from Argonne to Starlight is an internet exchange point that is in downtown Chicago. That's a little bit longer. That is actually taking a circuitous route. So that's about 50 miles. That still can be used for quantum communication, right? So we have that, and then from Starlight there is a dark fiber going into Northwestern. So we have like a relatively complicated or relatively large metropolitan scale network. So we are still working on more demonstrations, but what we've done so far is we were able to distribute entanglement between argon and Fermi, right? Likewise, northwestern guys were able to distribute entanglement between northwestern and starlight. So, and then one other thing that we did was I talked about like the demonstrations that we did within argon. So this is a midway point between argon and Fermilab. So when that link had some issues in the last mile, so during that time we were able to loop through that midway point and get it back to argon. So this is one of the first entanglement distribution that we showed, what we call as argon quantum link that goes outside argon and coming back. And then once that problem, the last mile problem was fixed, what we did was we were able to distribute entanglement between argon and Fermi, and we were also able to send some classical signal on the same link, same fiber. So what we did was we used, there is this multiple bands in the telegram fibers, right? So there is C band, O band, and C band is primarily used for classical communication. So what we did in this case was we used C band for quantum and used O band for classical, mainly because the attenuation is less on the C band. So we were able to show that we passed clock signals on O band and quantum signals on the C band, and we were able to show that still we were able to distribute the entanglement. So it's not just us, there are like several other people all over the world. There have been some demonstration between Italy and Spain, I believe, and then China has done some demonstrations, and there is also the Calgary, Netherlands have done some demonstrations as well, like similar to what we've done. And then this Calgary experiment is what actually showed the teleportation. Like they were able to teleport the quantum state in a campus scale, like 8-kilometer network. And then Oak Ridge National Lab has also done some demonstrations. So the thing, they've done, like a lot of people have done this demonstration. So what's the limitation, or what are the challenges, right? So all these demonstrations are mostly point to point. Not mostly, all of them are point to point, right? But if you guys are experts in networking, and some people actually don't really consider the point to point link as a network, right? So you need to have at least 3 nodes or more nodes to call something as a network, right? So we want to go beyond that point to point. So we want to go like use multiple nodes, demonstrate distribute entanglement between multiple nodes, and also move state, teleport state among multiple nodes, right? So that's something that we need. And also these demonstrations are carefully calibrated or manually done, right? So a lot of manual steps involved. So we really need to automate these things, right? So how do we actually automate these things? Because the thing is, these demonstrations, in some sense, they are lab demonstrations. These are all like pretty much like physics experiments. So we want to move them out of the physics experiment and make it into like network experiments, right? So, but the thing is, there is no clear abstraction on how do we actually interact with these devices, right? So there is entangled photon source, there is single photon detectors. So how do we interact with them? So we need to create the abstractions, and also the devices are also not there, right? There is no quantum repeater, there is no quantum memory, but even the devices that exist, we need the abstraction. So we want to develop a control plane that is fully automated, right? And also, like I talked about multi-node, and we also should be able to support multiple entanglement distributions, which sort of simulates multiple users. So when the network becomes real, you want multiple users to use that network, right? So we want to support multiple users, and then we want to go, so even though we've done some simple demonstrations in the metropolitan scale, so we want to do more, and then we want to go beyond metropolitan to regional scale. So this is a new project at Argonne. We're calling it as InterConnect, right? So the idea behind this is to address some of the challenges that I mentioned, right? So we want to be able to fully automate the entanglement distribution, right? And also I mean, there are, I mean, scalability along multiple dimensions, right? So I mentioned about this point-to-point, and also I mentioned that all these demonstrations are at the photonic qubit level, right? So we want to go beyond the photonic qubit to incorporate matter qubits, right? So that's why we call it as a heterogeneous network, right? So we want to connect different platforms and enable people to distribute entanglement between platforms and eventually move the quantum state between different platforms. So there are two key components in this project. So the first one, we call it inter-QNet achieve. So this is where I talked about three different platforms, right? I mean, so those are the three key platforms. There's superconducting qubits, ion-trapped qubits, and neutral atoms, right? So luckily, we have physicists at Argonne working on these three different platforms, and there are also collaborators who are working on similar platforms as well, right? I mean, so we, in collaboration with other institutions like University of Chicago, University of Illinois at Urbana-Champaign, and Fermilab. So our goal is to basically, so even though we have that Argonne quantum network which connects these different platforms, we still not able to distribute entanglement between different platforms yet, right? So our goal as part of this project is to enable that entanglement distribution among these different platforms. But there are several challenges with that, right? I'll talk about those challenges and our plan to address them, right? So Shu Han is a colleague who actually is working on the superconducting devices. The problem with these different matter qubit platforms and the photonic network is that, like I said, so we've demonstrated, people have demonstrated this quantum communication or entanglement distribution in the C-band, right, which is 1520 to 1550 nanometers, something, somewhere around that range, right? So, but then these superconducting platform produce microwave qubits which are at a different wavelength, right? So which means that we need to do frequency conversion. And in other words, I mean, there's a process called transduction that needs to happen, which can actually convert these microwave qubits to photonic qubits, right? And that's not easy. There are a lot of challenges, and they're still fabricating devices that can actually aid with that process. So that's something that's ongoing. And likewise, so this one is actually, at least from that point of view, this one is easy in the sense that this has a transition, erbium ions, when you actually pass the laser through it. I mean, it has an excitation, so it can actually excite photon in the C-band, right? It can excite the photon in the 1520 nanometer, right? So from that perspective, this is easy. But then again, like fabricating that device, there are challenges. We know it can actually produce that, but in order to make it reliably produce that, it's not easy. So it's still trying out different materials to enable that in a reliable fashion, right? Then the third one is the ytterbium atoms, right? Ytterbium atoms, again, there are three people working on it. There is an Argonne physicist and a person at University of Illinois and University of Chicago. So this one, interestingly, this has an excitation in 1389 nanometer, right? So which is closer to the C-band, but we still need to, so it can actually have that excitation in 1389. But again, when it's excited, how long it can remain in that state, right? I mean, so that again, that coherence time is very less. So there is challenge in that, like, so how long we can actually maintain that state, and also, like, how do we actually convert that from 1389 to the C-band, right? So for that, we again need a quantum frequency converter. So we have another collaborator, Prem Kumar at Northwestern University. So he's working on the quantum frequency conversion. So wherein we can actually convert that 1389 to 1520, right? So then the idea is basically, so you have an ytterbium atom, erbium ion, and superconducting microwave qubits, right? So basically you excite them, you get a photon out of it, right? So which means that you produce a photon that is entangled with an ytterbium atom. You produce another photon that's entangled with erbium ion, another photon that's entangled with microwave qubit, right? And then you actually do a bell-shaped measurement on these photons. Basically, you get these two photons, you entangle these two photons. Through that, you can actually entangle. Say, for example, the photon that comes out of the erbium ion and the photon that comes out of the ytterbium atom, you make those two photons entangled, and through that, you make the ytterbium atom and the erbium ion entangled with each other. So that's the basic idea. So I talked about this a little bit. So for all the demonstrations that has happened, there are a lot of manual steps, right? So you need to do several steps. Like there are multiple nodes involved. You send in a signal to a node. You get that node to do something. So that all has been done manually, so which we want to actually orchestrate it through an orchestrator to get to make this in an automated fashion, to basically make it a routine process, right? I mean, so if manual effort means, I mean, you have to have someone who actually, I mean, monitors these things and logs into different systems and do that. So first step, what we want to do is at least, I mean, script that steps out, right? And then we look at what other challenges we have and automate it one by one. So, so that's sort of the device level things, right? I mean, so that's the lower level, device level things. How do we connect and what's the plan for it? And you also need to be looking at the software stack or the architecture, a higher level architecture for scalable quantum networks. How do you actually develop one, right? The issue here is that since we have an example in the classical networking case, right? I mean, so because we have a classical internet, we have the software stack, we have an architecture. So we have 7-layer OSI stack. So we have a 5-layer TCP/IP stack, right? So what people are doing is, oh, okay, so we have that. Let's just use the same architecture, right? Let's just have that 5-layer architecture. Let's just have that 7-layer architecture, and let's try to fit in to the quantum communication, right? So what we believe is that that's fundamentally problematic, because there are a lot of difference between the classical communication and quantum communication. You don't want to blindly replicate the classical architecture, just adopt that for quantum communication, right? So this is an example kind of layered architecture or different planes that we came up with for one of the projects. But I'm not in any fashion advocating that this is the way to go, but this is one sample architecture, right? But what we argue is that the key thing that kicked off the classical internet, right? The classical networking is this hourglass-shaped architecture, hourglass-shaped model, right? So there is the neck in the hourglass, and that's the IP in the classical networks, right? So different types of devices, they all speak the IP protocol, right? I mean, so there is a interface that you get from all the devices. They provide the IP interface, right? Likewise, different applications, right? All of them can make use of that IP interface to talk to these different devices, right? I mean, so there are other layers in that stack, but that's to simplify it. So that's fundamentally made it like any kind of device can get on the network, right? I mean, as long as they speak IP, right? So likewise, can we adopt a similar hourglass type architecture, right? I mean, so at least that's something that we are advocating. We think that the hourglass model will help with the quantum communication, quantum network architecture, but we still need to do research on what is that neck going to be here. Like IP, what is it? Is it the entanglement distribution, or is it something else, right? So we want to do that research as well. So this forms the crux of the second piece of the InterQNet project, right? So I mentioned InterQNet project. InterQNet project Achieve deals with the physical network that can enable communication between different platforms. And then there is a InterQNet scale part where we want to develop a scalable architecture, or where we want to at least study different scalable architectures, right? But there is a fundamental problem, right? How do we actually study this scalable architecture? I mentioned that the quantum network, the real quantum network, is in a very preliminary state, right? There are not many devices available. So I mentioned that you cannot amplify the quantum signals. In order to amplify quantum signals, you cannot pass through the regular classical amplifiers. You need quantum repeater, right? But, so quantum repeater, people have actually developed theoretical models for it. So there are 3 generations of quantum repeaters that have been proposed, but there is no quantum repeater in practice available yet. A lot of people are trying to build one, and we are trying to build one too. We believe that the ytterbium atom platform that I mentioned is a good platform for quantum repeater, so we are actually trying to build that. But all of the quantum repeater work is still in preliminary state, right? So we don't need a quantum repeater. So how do you actually do scalability studies? And so if you want to do scalability studies, you want to scale the distance, you want to scale in terms of, again, like the heterogeneous platforms. I mean, I mentioned about the heterogeneous platforms, but it's still very preliminary, right? How do we actually conduct large-scale experiments to study like what kind of architecture would be good for quantum communication, right? So that brings us to like what happened with the classical network, right? So the classical network, if you look at the classical network, simulations played a huge role, right? So there was this NS series of simulators, right? Network simulators, which won a huge award actually. Don't know if I mentioned it in here, but they won an award like few years ago in terms of like, so for the role that it played in shaping up the classical internet, right? So what it helped was, so there were different protocols. So if you look at TCP, it has evolved significantly, right? I mean, so the additive increase multiplicative decrease based congestion control algorithm went through a lot of iterations, right? So different TCP protocols, different kind of lower level technologies, right? I mean, ATM, SONET, and all those things. So the simulators actually played a huge role in evaluating the pros and cons of these different platforms, different architectures, different protocols, right? So likewise, what we argue is that simulators can play a huge role in the evolution of quantum networks as well, right? Because you have a lot of different choices. So if you look at memory, there are so many different choices. Quantum repeaters, different choices. Error correction protocols, many different choices. So, and then again, qubit platforms, there are many different qubit platforms, many different protocols to distribute entanglement. So all of these can be studied through a simulator, right? So, I mean, this just talks about like different advantages of the simulator, what all you can do. So you can, like I said, I mean, you can do the, study the architecture design. You can actually find alternates in terms of for the platforms. So there are many different advantages, many different things that you can do with the simulator. So that brings us to our work in this space, right? So, I mean, my background is in classical networking, and I did some research in classical networking, but I was actually a user of all the latest and greatest in the networking, all the technologies that you guys build. So I'm a user of it, and like in a lot of cases, early user of it, right? So my background is primarily in, I mean, I knew the classical networking quite well. And about 6 years ago, in the US Department of Energy, they started talking about quantum networks, right? And they did a first workshop, and I attended that first workshop, and then, I mean, at that time, I didn't know anything about quantum. I mean, even now I only know little, but at that time I didn't know anything. And I was thinking, how do I contribute to this quantum networking effort, right? So that's where, like, okay, the simulator is probably the early step that I can do. And after that, we started thinking about the simulator. We started slowly building the simulator. It's called Sequence. Now it has actually evolved quite a bit. I mean, it's an open source project. There are users for it from several countries. I mean, I would encourage you guys to take a look at it. I mean, if you see a need for, like, if you want to play with how quantum communications work, this is a good starting point. So we did a modular design. Basically, you need hardware models, right? So there are devices. What are the key devices? Photon source. You need to create entangled photons. So you need to have an entangled photon source, a model for it. You need to detect that photons. You need to have a model for it. And you need a memory. Because the thing is, you want to scale it, so you need the repeater. So since there are theoretical models for it, we implemented those models, even though real physical device is not available, right? So those are the bottommost thing forms the models, and then you have some protocols. So there are protocols to distribute entanglement. So we implemented those protocols, and then you need to manage the resources. There is a resource manager piece, and then you need applications. So there is QKD, well-known or well-established application. So that's there. So we implemented some applications. We implemented both network-level protocols, application-level protocols. So that's all available in Sequence. And then, so basically what you can do is you can feed in a network topology. You can basically set the properties of the optical components. So there are simple models for fibers, models for classical communication, and then you can actually choose the protocols. There are protocols that are available. There are protocols that are contributed by people, the protocol that we developed. So all of them are available in the Sequence simulator. And then what we did was we did some experiments. We tried to mimic this metropolitan scale network that I talked about. So we did that. And then what we realized was, when we actually started to scale, when we actually increased the traffic, when we increased the number of users, when we increased the number of nodes, we ran into scalability issues with the simulator. So we parallelized the simulator as well, so it can actually use a cluster of nodes and run faster. So that's also there. Yeah, I mean, the parallelization gives a decent speed up. I'm not going to go into the details of it. So what you can actually do with it, right? So I talked about some architectural design choices. So what could be that, right? So we still don't know how do we actually pass the controls in a quantum network, right? I mean, so the demonstrations that we have done so far is by doing out-of-band control. Like you send control signals out of band to these devices and have them actually distribute entanglement and transfer or teleport state. But you can also do in-band, right? So doing in-band control is tricky. So you need to have timing synchronization. But that's something that you can study in the simulator, right? I mean, so you can actually have an in-band control versus out-of-band control, implement both of them and study the pros and cons of it, what are the trade-offs involved in it. And one other thing that we also did in the simulator is that, I mean, entanglement is a key resource in quantum network. Can we actually pre-generate entanglements so that when a request comes in, so basically when a request comes in to create entanglement between A and B could be at a longer distance, right? So you need to have like entanglements at smaller length. So there is an intermediate node at C, you create entanglement from A to C and C to B. So this, I didn't really talk about it. So you can actually create like smaller entanglements to create a long distance entanglement. So you can use multiple small distance entanglements, and there is a concept called entanglement swapping. So you have entanglement between A and B, you have entanglement between B and C, and if you actually do a measurement at B, if you try to entangle those two particles, you actually get an entanglement between A and C. So using that, you can actually form a longer distance entanglement. So since you have to do that, And entanglement generation is a probabilistic process. Like I said in the beginning, everything in quantum is probabilistic. So you need to, I mean, when a request comes in and then you try to generate the entanglement, it can take longer time, right? So you want to like adaptively pre-generate entanglements. So that's something that we've done. So with that, I will summarize and be happy to take questions and have some discussion. So quantum networks hold a lot of promise, but things are still in a very preliminary state, and the quantum network devices and protocols are under active development. There's several campus scale demonstrations that have been done, and metropolitan scale demonstrations as well. Like I showed, we have done some demonstrations, other groups have done some demonstrations, but scalability has emerged as a key challenge now. And the interconnect project that we have at Argonne addresses scalability in different dimensions. And there is the sequence simulator, because we cannot do all the study in practice and real experiments. So sequence simulator provides an easy tool for doing the scalability studies. So with that, I will close, and I'm happy to take questions.
Question? Anybody question for the quantum network?
Hello. Nice to listen to your presentation. It was very good and very informative. I don't know much about the quantum computer, as you have also described it's at very early stage. I was just wondering about the communication, like why you are going for quantum communication, as you have already very good classical networks, like you are using fiber and you're trying to transmit the photons over the fiber. We already have a DWDM and other kind of multiplexing techniques which are transmitting the light over the fiber. But on the computers, we are working with the electrical signals, okay? And then they are converted into the light and multiplex over the fiber. So, like, definitely there would be a reason, and I want to ask that reason, why you want to develop quantum networks which are different than the classical networks. And one thing you mentioned is that, like, if you are using quantum networks, still the speed would not be more than the speed of light, okay? So I want to ask what thing you are referring that would be more than the speed of light in the quantum communication or a quantum network that you that would be in your mind or with your knowledge? Yeah.
Well, I'm not sure if we can actually transfer data faster than light anytime soon, right? So the thing with quantum networks is you are able to transfer the quantum state. If you want to preserve the quantum state. So that's why the classical, so you cannot actually send that as classical information, right? So that's primarily the reason. So again, to your question about like, so what could be the uses for it? So what are the advantages for it, right? I mean, so the near-term advantages are, I mean, my personal opinion is actually in sensing, right? So quantum sensing, distributed quantum sensing, I feel that that's a low-hanging fruit, but still for that we need quantum sensors, right? So the quantum computer, distributed quantum computer is another thing. So where you are able to create a big quantum computer, and for that you need to be able to transmit quantum state between the computers, right? So that's another use case. But again, it's still not clear as to like, so this network and these repeaters, so since they're like still very preliminary, it's actually hard to gauge the advantage, right? I mean, so do you really get the advantage when you actually combine these multiple quantum computers? I mean, in order to get the advantage, what are the capabilities that the underlying infrastructure that you need to provide, right? So we still, I mean, we are trying to ask that question, but we are asking that question by doing simulation, right? And doing the simulation, but we're trying to validate that simulator using whatever infrastructure that we have, right? So we have very small scale infrastructure, and we validate that simulator using that infrastructure and try to scale it up, right? And that can only be so good. I mean, it cannot, I mean, when the real infrastructure scales up, will the simulator, whatever the simulator predicted, will that match with it? We don't know, but this is the best that we can do now, right? So.
Just a small thing. You said like you want to use, like the quantum network is developed because you want to preserve this entanglement state. So as we do in the classical network, if you want to move from electrical signal to the optical signal, we convert that, encode that information into another state, and then we decode it on the other end. So why we can't do this here? Because like you said, the probability are associated with the entanglement state or some information. So why we cannot encode that information and then regenerate that state at the receiver end?
So the idea is that the quantum state has more information than classical. So that's why it's hard to actually encode that state using classical signals.
Okay, thank you, Dr. Lazi. Yes, please clap again to our Dr. Lazi.
Oh, thanks.
Yes.
Thank you.
And he is keynote speaker.
Thanks so much.
Okay, thank you.
All right. Thanks, everyone.
Next presenter is Dr. Kim. Kim, are you there?
Hi.
Oh, hi. Wait a minute. Please change it. Dr. Kim is talking about this index technology. Index technologies include the inter-data centers is big data transfer, how the architecture and how the policy, how transmission, and how the related the networking engineering work. He working for this KIST and the Korea in Korea. And please, are you ready? Please go ahead with your presentation.
My name is Kyu Kim from KIST, and today I'll be presenting our latest initiative, the National Data Exchange Node, or NDEX, as a part of APRP workshop. This project is a significant step forward in Korea's data infrastructure, aiming to facilitate the secure and efficient exchange of large-scale data across various sectors. Here's the agenda for today's presentation. First, I will explain what a data exchange node is and why it's needed. After that, I will share the result of our demand survey. Finally, I will introduce you to KIST's NDEX project and discuss our goals and future plans. Let's start by defining what a data exchange node is. Unlike traditional internet exchange points, which handle internet traffic, data exchange nodes are designed specifically for the direct interconnection of data networks. This allows for the high-speed transmission and processing of large-scale public and research data, bypassing the usual bottlenecks associated with traditional internet exchanges. I will explain the concept of a data exchange node by comparing it with the existing internet exchange system. This figure is the current internet exchange structure in Korea. ISPs, Internet Service Providers, and Korean Research Network, KREONET, are connected through several internet exchange points. Most internet traffic originates from data centers of content providers or cloud services. If this traffic crosses different network operators' domains, it needs to be interconnected via internet exchange points. The large-scale data traffic generated by research data, such as some raw data for AI training, they causes significant bottlenecks when passing through IXPs, internet exchanges, leading to congestion and reduced service quality. So both sides are struggling with the largest research data traffic. Network providers are suffered by the bottleneck of IXPs, and the researchers are suffered by throughput and reliability issues, especially when they using commercial clouds. The key difference of our solution is that data exchange nodes does not handle regular internet traffic. Instead, the data exchange node links various data networks directly to ensure fast and secure data transfers. This is particularly crucial for research data, which can be very large and sensitive. Another advantage of this structure is that it is physically separated from the internet network, thereby reducing the risk of security attacks. Currently, Korea lacks the infrastructure necessary for the secure and efficient exchange of large-scale data. This leads to significant burdens on traditional internet exchange points and creates challenges in sharing and utilizing research data between the public and private sectors. Our goal with Index is to create a dedicated infrastructure for large-scale data exchange, which improve data utilization and reduce bottlenecks and enhance security. In this chapter, in 2023, we conducted a survey to assess the demand for a data exchange node infrastructure and service in Korea. The survey targeted advanced researchers and general users from institutions affiliated with CREONET, aiming to understand their needs and the potential benefits of a national data exchange infrastructure. The survey aimed to assess the potential benefits of establishing a national data exchange node and its impact on researchers in various fields. Each survey period is about 2 months, and survey method is online web-based survey. So the survey is conducted by the Informatech and KRI, and survey participants are 39 advanced researchers in Korea. They are in national core advanced research fields such as astronomy, high-energy physics, and climate science. And there are also 91 general users. The general users are IT managers from institutions affiliated with CREONET. The survey results revealed the high demand for faster data transfer speeds, particularly among researchers dealing with large-scale data. Additionally, IT managers were significant concerns about information security, throughput and security. So the IT managers were significant concerns about information security, which further supports the need for a dedicated network separated from the public internet for research data. And respondents indicated that the establishment of Index would significantly enhance the utilization of CREONET, particularly with features like network accessible storage and disaster recovery. We expect that Index will increase the efficiency of data sharing and collaboration among researchers. Network access storage and backup and disaster recovery. Now I would like to introduce you to KIST's National Data Exchange Node, or Index, detailing its objectives and progress made in the past year, current efforts and future vision. The Index project is designed to address the challenges we've discussed and to build a dedicated infrastructure for large-scale data exchange in Korea. The Index project is structured around 3 main components. First is infrastructure development, and second is core technology research and development, and the final is the establishment of an operational center. This structure will ensure that the Index system is robust, secure, and capable of handling the demands for large-scale data exchange. And this project is divided into 2 pages. The first page, from 2023 to 2024, focuses on designing the piloting the system. And the second page from 2025 to 2026 will involve scaling and stabilizing the infrastructure and expanding our network to cover 3 major metropolitan areas and integrating with telecom data centers. The index project is structured around 3 main components: infrastructure development, core technology research development, and establishment of an open area center. The index infrastructure includes the establishment of regional nodes across Korea. We completed the first pilot node in Busan in 2023, and this year we are focusing on building a new node in the Seoul metropolitan area. By 2026, we plan to connect these nodes with international data exchange networks. Each of the exchange nodes requires optical equipment and switches and routers and management equipment and UPS and so on. Last year, we built the first exchange node infrastructure in Busan. The pilot node in Busan was strategically located near international submarine cable landing stations to ensure global connectivity. This node plays a crucial role in the index network, serving as a key point for both domestic and international data exchange. Currently, 4 networks of Creonet 2, NHN Gwangju AI Data Center, and GIST HPC AI Public Infrastructure AI in Korea are linked to the index. By 2026, about 20 data centers, including commercial clouds and supercomputing networks, will be linked to about 100 gigabit to 400 gigabps with the index. We expect that the index will help the research activities of more than 200 public and research institutes and related researchers of Creonet. And next, this is our index development direction for our future. Our long-term vision for index is evolve it into a comprehensive data exchange platform. This platform would not only support network infrastructure, but also enable data services and transactions, helping to create a more integrated and efficient data ecosystem in Korea. We also aim to position the Busan node as a global open network exchange hub for the Asia-Pacific region. This will involve connecting with other major global nodes, facilitating international research collaboration and data sharing. So, in conclusion, I'd like to highlight the key differences between data exchange nodes and internet exchange nodes. While internet exchange nodes are focused on general internet traffic, data exchange nodes are designed specifically for the large-scale data exchange, making them essential for the secure and efficient transmission of research and public data. We believe that index will play a crucial role in advancing Korean data infrastructure and look forward to your support and collaboration in this important initiative. Thank you for your attention.
Thank you, Dr. Kim, and we don't have enough time to the Q&A. Sorry about that. Thank you.
Thank you.
And the last presenter is me, and I just the use is 5 minutes more. So, okay, Dr. Kim, thank you. Yeah, please change
Thank
the
you.
presentation files of mine. Yes, my title is the data sharing infrastructures across the Northeast Asia, the supercomputing centers for open science and the KRP status. And I want to skip the background of CREONET and what is CREONET and the KRP status in Korea. And we have a vision for this develop this national science infrastructure to make upgrade. And this is the real, the steps is how to deploy or apply for our supercomputing data center, something like that. Yeah, this is the Korea research platforms is the architecture and how to work in this, the part of the 3 or 4 sections. And I want to explain about the focus of this project. Related project is A3. A3 meaning is ASEAN countries, Korea, China, Japan, the 4-side program. The name is, as I first mentioned about that. So this project is belong to the APRP working groups. It's the first project is from the TAIN and Asia Connect project. As you know, the name is building on the high bandwidth distributed HPC. The reason proposal to the TAIN and the public international public fund, how to make infrastructure or the research platform based on the high bandwidth environment, such like NN, the PAN, the CREONET, TAIN, or APAN, to provide the member of the APAN in order to the smart brains is running their Python code and running the GPU program and something like that. And every country is not equal to using the IT infrastructure. And some advanced countries can donate the partially the computer resources. As the container technologies is very essential for those the projectors. So this project is the 3 countries is the proposed. Each country is a national the science foundation and together the world together award. So we got the totally this project. The main title is as I mentioned before, and the Korea subtitle is the research on the building high bandwidth distributed HPC based on the high compression metadata of AI technology. The participant countries Korea, Japan, China, and the duration is during this August of 2024 to July, bottom of July is 2029. And the budget is Korea in the $264,000, and Japan is $347,000. China is the $562,000. It's totally around this $1 million. And the PI and the co-PI, and this project is the PI is the Hidetomo the Kaneyama from Riken and Japan. The Riken Institute is the inventor and the operation is a K computer. And the Yutung Lu is he came from this China, and the co-PI of China, the NSCC, Guangzhou Supercomputing Center. As you know, the Guangzhou Supercomputing Center operation is a 1001 and the 1002 supercomputer. And the Korea is on me and from KIST in Korea. And the objective, the final goal is described in the boxes. According to these boundaries of the advancement of science and technology, though the LLM or the large-scale language model and the advancement of the science and technology without binaries through the open science. This project is aimed to lead the development of an advanced research environment, system, and element technology for the utilization and the sharing of research data, and to establish the infrastructure for sharing advanced research data between Korea, China, and Japan. And those that pictures is the basically the architectures is between among the three countries, what we need and what we built. And this is our project is a strategy. That we divide into the 4 units. The first unit is the infrastructure unit, the leading by China, and the second unit, the data transfer, the leading by Korea. It means that the science DMG and the big data transfers, what we the talking is so far in APRP working group. And the unit 3 is the data compression part, reading by Japan. Unit 4 is a metadata unit, reading by Japan. The below box is how to the combination, each unit is to make a promote is the support our the goal of this project's aim. And the more detailed technologies, so what technologies is combined each unit? And the first unit is the infrastructure unit, the data sharing file system across 80 supercomputing centers, and the data placement optimization and the fast access, and the HPC environment building and the integrations. Chinese are always is wondering about they have the, several and a lot of supercomputing centers is distributed, but all supercomputer centers is running a standalone. It means that is isolation. But at this case, they want to build to make this the link, the high bandwidth research network, and they want to using the big one supercomputer. At that time, it's the following the technologies, how to build a file system and how to transmission the big data, how to communicate the CPU and the GPU combinations. The unit 2 is the data transfer units, is the core technology, science DMG network deployment and accelerating of the long distance transfers, and finally is build a mutual trust zone and the secure transmissions. The unit 3 is the data compression reading by the Japan, the lightweight data compression technology, and the AI-based compression algorithms. It means the AI algorithm deployed for the how to make the index areas. We can call it metadata. And the third technology is a TEGIP, the extension. Already the invent is the prototypes is how to the compression data through this TEGIP technology. The unit 4 is metadata unit reading by Japan also. The FAIR metadata design. The FAIR is the suggestion by this the global the community of the how to metadata is make this the efficiency for the file system. And the second thing is cross-disciplinary and international models, and finally open science support. And so those technologies, combinations each unit, and to make the further technology models to support our the A3 project is the aims. Conclusion is the 3 categories. The first one is HPC over HPN. It comes from this Korea status. HPC and over HPN. HPN means a high performance network. The Korea is a 25 government-funded national institute. Already they have the high-speed research network installed. We want to using the big data infrastructure and make the sharing or distributed HPC or super facilities they have. So, and then, and the A3 project is the involve or the many the institutes, the unique facility or supercomputers to share or the big coverage, make the big coverage to their research areas, and make this upgrade the utilization and the deeply collaboration. The currently deeply collaboration is the very beginning steps. It's just communicating email or some this transmission and exchange data. But deeply the collaboration is the running on the system level. It's all kind of this automatically the layers. So all those kind of things is the detailed expression of the conclusion part. So after all, and the APRP and the high bandwidth is distributed HPC like or the super facilities is very important to the fair upgrade. A fair upgrade is all research domains in ASEAN regions. So APRP working group and such like those projects the finally support our aim and our dreams and visions. Thank you for your listening. And sorry for over the 15 minutes, and could you please out there enjoying the break time. And we restart again at 11 o'clock. Thank you.